And we were going to transition from talking about simple fatty acids to what we call fats and oils. So fats and oils. And does anyone remember what fats and oils were from? I'm going to say chapter 25 is a stab in the dark on carboxylic acids and esters. What is a fat or an oil? Yeah, it's an ester of glycerol plus 3 fatty acids. And remember, what are fatty acids really? They're just carboxylic acids, right? And glycerol is just an alcohol. And so really, the formation or the makings of fats and oils is just the esterification reaction we learned way back in chapter 25. So we take glycerol, and I don't know, I guess if I'm drawing it as a line drawing, it kind of looks like this. Where remember, these are carbons right here. So it's so glycerol is a 3-carbon molecule with 3 OH groups on it. And then we add 3 fatty acids to it. So here's a fatty acid. Now, I'm not going to worry about how many carbons I'm showing on these fatty acid chains. They can be the same, they can be different, they can be saturated or unsaturated, meaning they can have carbon-carbon double bonds in them. What we're really focusing on here is sort of what we're drawing or how we're drawing it and the reaction that's occurring. And you know, in the homework or on a test where you're told to use a specific one like palmitic acid or oleic acid or something like that, then make sure you use the right parts. But to illustrate simply what's occurring, we simply need 3 fatty acids. So of course we're going to lose H2O in this reaction. It's a dehydration. And where does that H2O come from? So it comes from the OH and an H from each of the alcohols and a carboxylic acid. Remember, it doesn't really matter which way you think about it, whether the OH comes from the alcohol and the H comes from the carboxylic acid, or the OH comes from the carboxylic acid and the H comes from something else. It's all about the same thing. And so if we connect them all together, then we get a fat or oil, and notice that it really is just a giant ester. And in fact, there's 3 ester groups in it. And again, I'm not being terribly careful with how I draw the fats. I did draw one in there with a double bond. I'm not even sure I put the double bond in the same spot. It doesn't move, but I'm too lazy to count over. And then of course we would have plus 3H2O in this case because we have 3 water molecules that we had to remove in order to make that fat or oil. Now, what would happen if I wanted to break apart a fat? Yeah, we can, remember, do the reverse reaction where we would simply add H2O. And so in one direction we have a dehydration. In the other direction we have a hydrolysis. And I remember reminding you guys when we first covered dehydration and hydrolysis reactions that the majority of the reactions that we look at in the biochemistry chapters are simply dehydration and hydrolysis reactions. And so you remember we had a dehydration or a hydrolysis reaction in our carbohydrate chapter 2. What type of bond did that form? So if I react 2 carbohydrates together, or I should say maybe be more specific, if I react 2 monosaccharides together and we lost water, then we would make what type of bond? Sounds like a good question to look up because I guarantee you that one's on the test always. Okay, so the main difference between fats and oils then is not their structure. Well, I guess it is because we use different molecules for each. But remember, fats are considered solids at room temperatures, whereas oils are liquids at room temperature. And that really is sort of the biggest difference that we have to look at. Why do I have... Some days I wonder about myself. even in my little notes here I made for you guys, I've got random errors kind of cropping up everywhere. We have another name for these. Sometimes we call these triacyl glycerols. And of course the tri means there's 3 fatty acids. The glycerols kind of saying that we make it out of a glycerol. Or sometimes you'll also see this called a triglyceride. So again, biologists have different names than we have for things quite often. Now, one of the fundamental properties of all the molecules in this chapter is that they're hydrophobic, right? So what part of this molecule is hydrophobic? Yeah, this end of the molecule is hydrophobic with all these chains. Whereas this front part of the molecule where we've got those oxygens and those carbonyls, that's a little bit hydrophilic. And in the case of a fat or an oil, it's really not much. If we want to make that more hydrophilic, we need to add sort of more pieces to that. And then the other thing you should realize is that you'll see these drawn all sorts of different ways. Sometimes they flip the center one around so it's facing the opposite direction so that you would get a molecule that looks like this. You know, sometimes they'll flip one of them around because if you look at it and you draw it out, that's actually the way it looks. So don't be surprised if you're looking in the book or you're looking on a website that they occasionally draw them different ways. However, I would say that that's the most common way to draw a fatty acid. Some other things about, not fatty acids, I'm sorry, about a fat or an oil. Some other things that we can talk about for these is we can take a look at their metabolism. Is that green color any good? Looks pretty on my board, but it kind of looks ugly on yours, I think, or not as pretty. And so if we take a look at this, fats and oils, and we can compare and contrast them versus carbohydrates. And if we look at it, it really sort of depends on your diet how much of the energy that you generally get from fats and oils in your diet versus carbohydrates in your diet. But if we take a look at specifically, you know, a single fat or oil molecule or a single carbohydrate molecule, you get about 9.5 kcals per gram or 40 kilojoules per gram of energy when oxidized completely. And I should point out that we'll come back to these numbers, figures, and we'll talk more in depth and detail about it when we talk about the bioenergetics chapter. And so this is sort of an intermediate level. We're just going to throw a couple facts at you. I'll actually go into it in more detail probably right now than we need to, just so that when we get to the bioenergetics chapter, you'll have seen it twice. Carbohydrates, on the other hand, have about 4.5 kcals per gram, or about 20 kilojoules per gram when oxidized. And so fats and oils have about twice as much energy content. Does anyone know why they have so much more energy in them? So what do you guys remember about oxidation reduction reactions? If something's oxidized, what happens? We what? Gain bonds to oxygen. That's one thing. There's still more, and I saw some of you listed on the homework, so I know someone out there has the answer in their head. So if I oxidize something, I gain bonds to oxygen, I lose bonds to hydrogen, I lose electrons, Leo the lion goes grr. And what's the fourth one? I release energy, right? And so then the opposite, if I reduce something, I'm losing bonds to oxygen, right? Gaining bonds to hydrogen, gaining electrons, and storing energy. So something that has very few bonds to oxygen and lots of bonds to hydrogen stores lots of energy. Or basically, the more reduced something is, the more energy it stores, and the more oxidized it is, the less energy it stores. So this is more reduced. This we would say is more oxidized. Because if we take a look at a fat and an oil, now if we ignore the carboxylic acid end, because that's kind of the exception to it, right? Meaning most of these carbon atoms simply have a bond to two hydrogen atoms and then bonds to other carbons. Whereas if we compare that to a carbohydrate, 1, 2, 3, 4, 5, 6, we've got an aldehyde on one end, and then every single one of these has an OH bonded to it, right? And so if we take a look at an atom of a fat and an oil, and we compare that to a kind of the average atom on a carboxylic acid, notice that the fat or oil has two bonds to hydrogen. The carbohydrate has one bond to oxygen and one bond to hydrogen. You guys remember how we calculate oxidation numbers? We discussed this, I don't know, probably way back in chapter 22 or 23 or something when we were talking about alcohols, because that was our first sort of oxidized molecules, the first time we did oxidation reduction reactions. Does anyone remember that? So oxidation numbers. And we'll have oxidation numbers over here. And then off to the side, because we don't want to do that there, the general rule, remember, is that oxygens have a -2 charge, hydrogens have a +1 charge. And then carbon is where it's variable, meaning that's where we have to do the work. So if I take a look at my fat and oil, and I've got a molecule that looks like this, and we could ignore the carbon-carbon bonds because that's the same in both molecules, right? If hydrogens are +1, +1, +1, +1, +1, and oxygens are -2, what I'm really saying is, what is the oxidation number of the average carbon on a carbohydrate versus the average carbon on a fat or an oil? What does the carbon on the fat and oil side look like? So if the hydrogens are +1, the carbon has to be a -2, right? Because remember, the sum of the oxidation numbers has to be 0. Or if it's a charged polyatomic or something like that, it has to be equal to the charge there. So what about the oxidation number of the carbohydrate? Well, add up the numbers. What's -2 + 1 + 1? 0, right? So if the overall charge has to be 0, and I've got an equal number of positives and negatives, then the charge on carbon has to be 0, whereas for the fat and oil, it has to be a -2. So we consider this to be more reduced, and this to be more oxidized in comparison with each other. And so the more reduced something is, the more energy it has. For instance, what molecule would have the most energy storage content, at least as far as these simple organic type molecules? What's going to have the most, well, most energy storage? I guess if I say it the other way, I'll give the answer away. Remember, what's going to store the most energy in it? What could we, like if we wanted to have a molecule and we just wanted to store the most energy in the most compact space in our body, what molecule should we choose? Now, obviously our body uses fats and oils, right? Because we'll learn the reason why is because the other molecule isn't terribly useful for us. But what molecule would have the most energy storage that we've encountered in life? Think about it. What's the most reduced? You guys have told me reduction means no bonds to oxygen, lots of bonds to hydrogen, right? So what molecule has the most bonds to hydrogen that you can think of? What? Yeah, alkanes. Or if we take it to the ultimate extreme, this is the most bonds to hydrogen that I can have, right? Here the carbon is going to have an oxidation number of -4. This, of course, is methane. What do we know it more for its common name? Natural gas, right? So if we could just store methane in ourselves, that would be probably the most reduced molecule that we could store. Now, what's wrong with methane compared to, say, a fat or an oil? At room temperature, methane's a gas. And so it would take a lot of energy to compress the gas down into a storable state. And really, it's a highly explosive, and it wouldn't really be a safe way for us physically to store energy. Now, we of course are more than happy to make tanks of, and usually we use propane if we're going to store it for long term, just because it's too hard to do the methane. But natural gas is a pretty well used energy source around here, and in fact, I would say a good chunk of the economy around here is simply based on extraction of methane from oil wells. What about the opposite end? So remember, this kind of goes here as the ultimate energy storage molecule. What's the molecule with the least amount of energy in it? We've already had this before. We covered this way back in chapter 22. So hopefully this is a review. And we'll cover it in the bioenergetics chapter. So it could show up on this test, could show up on the bioenergetics test, it could show up on both. I would say it's pretty unlikely that it'll show up on neither, though. So it's going to show up at some point. What's the most oxidized molecule that you can think of? Meaning it goes here in our list. So well, think what you did for methane. Lots of bonds to hydrogen, no bonds to oxygen. What's the opposite extreme? So what molecule does that make? Lots of bonds to oxygen. What's that? So notice here, this would have an oxidation state of +4. And so carbon dioxide is got the least amount of energy associated with it. In fact, when we burn something, if we burn an alkane in a dish, or we burn those alcohols, or we burned a fat and oil, what's the end products of all combustion reactions? Carbon dioxide and water, right? And we know that when we burn something, we release lots of energy. In this case, it's heat energy, or a flame. So carbon dioxide is the ultimate end product. What's the end product of all of Todd's metabolism chunks? The ultimate end product is always CO2, right? We breathe out CO2. We breathe in oxygen so that we can oxidize everything to CO2. We'll go through this, of course, in more detail when we do the bioenergetics, but I would guess that Todd's probably brought this up at some point, right? Whether it's in does he cover like this in Bio 111, Jess? Or Brittany? Yeah. What? Oh, so this is a little bit of a review then. So the other reason that fats and oils contain a lot more energy than carbohydrates, so kind of the second reason for that, is that if we take a look at a fat and an oil, it's 70% carbon by mass. 75. What did I say? Oh, sorry. And it's, oops, dropped my pen. Carbohydrates are only about 40% carbon by mass. So if you have an equal mass of fats and oils and an equal mass of carbohydrates, there's a lot more energy in that fat and oil. And that looks like that's about it for that section. Make sure I don't forget any little things. Nope. What was the next category for what we called simple lipids? So we had fatty acids, we've had fats and oils. The next one is waxes. And waxes are just gigantic esters. Gigantic esters. Now, I don't know, the word gigantic is a little bit on the non-descriptive side. I mean, it says big, but it doesn't tell us how big. Generally, if we take a look at a wax, the R groups are about 30 carbons long. And so when we say gigantic, we kind of mean gigantic, because when we were learning how to name esters and we were doing things with esters, we usually had like 5 or 6 carbons at most on one side or another. We're talking about having 30 plus on them. And so, of course, that makes them very hydrophobic. And in fact, hydrophobic. That's one of the reasons we tend to use them for wax coatings or sealants or for waterproofing. And quite often it's even found in nature on fur, feathers, skin, plant leaves, things like that. There's all sorts of different uses for it. And it's even used a lot in industrial uses. It's used a lot for cosmetics, for cleaners, conditioners, moisturizers, pesticides. We can even use waxes as industrial lubricants. And so waxes are really just giant esters, and that's all we're really going to cover for them. Other than that, they're not terribly exciting. Okay, our next big category was compound, or complex, is what I like to call them, lipids. And there's 3 categories of them. There's phospholipids, there's glycolipids, and I forget what the third one is off the top of my head. It's one of the new functional groups you stick on them. Phospholipids, there is glycolipids, and sphingolipids, that's my favorite one. Mostly because I like the word sphingo. It just kind of rolls off the tongue. And there's some things that these are all going to have in common, and there's of course some things that they're going to be different about. What I want you to know about each of these compounds is sort of what makes them up, how to build them, how to take them apart, meaning that's the chemistry type thing, and then we'll look a little bit about how their different shapes and the different functional groups on them allow them to have different physical and chemical properties. So for phospholipids, these are all made up of glycerol. They usually contain 2 fatty acids. They contain a phosphate group, which is just a phosphorus with a bunch of bonds to oxygen. And they usually form what is called a nitrogen base. And for the nitrogen bases, there's 3 basic ones. I should point out that you don't need to memorize any of these parts, right? You'll get, if you look on your cheat sheet, a picture of glycerol, you have a list of fatty acids, and you have a list of the 3 common nitrogen bases. Those are choline, and really the only reason we show a few examples is just so that you have a few things that you can look at. So you might see it drawn that way. You might also see it drawn like this, meaning a line structure. Then we have serine, and that is HOCH2CH-COO-NH3. And usually this has a positive charge and a minus charge. I guess let's draw them like we should to start with, and we'll show you why that happens. Or so if you were looking at that, and then the third one is ethanol amine. That's just HOCH2CH2NH2, and so that's just this right here with 2 carbons on it. So again, those are given on your cheat sheets. You can use those for whatever you want to do. Some details that J should fill in, because nitrogen has 4 bonds there, that should have a positive charge on it. And quite often for the serine and for the ethanolamine, they'll show that nitrogen having 4 bonds to hydrogen and or 3 bonds. So like for instance, you'll sometimes see ethanolamine drawn like this. And the reason is that in your body, it's very easy to find extra hydrogen ions or to lose hydrogen ions. And so what we find is that really in water and in water type environments and at the pH that our bodies are on, a lot of times those molecules are really drawn charged. And so you'll see them drawn both ways. Some books will draw it one way, some books will draw it the other way. And then for the serine, I ran out of room down there, so I'll put it up here. We actually form what is called a Zwitter ion. And you'll learn about those when we talk about amino acids, because serine is, of course, also an amino acid. And in that case, you'll actually gain a hydrogen on the nitrogen end, and you'll lose a hydrogen on the carboxylic acid end. And so for that molecule, you'll actually have a positive and a negative side to it. So all phospholipids are made up of those parts. And you have all of those parts given to you on the cheat sheet. So the only thing you have to do or remember is how they're stuck together. And so that's a list of the parts. Generally what we have is, if I kind of draw this as a, I don't know what you would call this. This is like a block diagram, I guess. Usually what we have is a glycerol, and then attached to it is a fatty acid, and attached to it is a fatty acid, and then attached to it is a PO4 group, and then attached to that PO4 group is our nitrogen base. Or sometimes you'll see that referred to as an amino alcohol, because it has both an amine group on it and an alcohol group on it. And then how we would build that if we were given all the parts is we take our glycerol, glycerol, and glycerol there. We take our fatty acid, and again, I'm not worried about what fatty acid I have, so just draw a bunch of carbons after it. Doesn't matter if it matches up or anything like that. And you can, of course, have double bonds in these too if you want. And then we have our phosphate group. And phosphate, before it reacts, starts off as something with 3 OH groups on it and a P. So notice that that really is just H3PO4. So what is that really? When we talk about phosphate groups, it's really just, what's H3PO4 from semester 1? Common acid that we should remember, phosphoric acid. And if we take our nitrogen base, we'll just take the easiest one. We'll do it like that. So we'll use ethanolamine. I will pause just a moment since it's a pain in the butt to draw these, right, Jess? Yep. So hard that you're not even drawing them. Yep. You're just focused on micro, huh? Jess is a very one-track girl, I've noticed. She does not multitask well. Why, just yesterday I saw her walking and trying to blow a bubble. Not good. She tripped, and I shouldn't say anything about coordination. Okay, so here what we're going to lose is we're going to lose a bunch of water. So if we take a look at where all the water molecules are, we're used to looking for this one because we've done our fatty acids and our glycerols. And then notice that if I have my phosphates, and then I can also get one between my ethanolamine and my phosphate. And so really, how many waters am I losing in this case? 4 of them, right? And then to stitch that all together, we simply go like this. So I've got my fatty acid, blah, blah, blah. Got my oxygen, or my other fatty acid, blah, blah, blah. Oh, there's a double bond in there. I've got an oxygen to a phosphate group. And then I've got that phosphate group connected to an amine group. And so there is our phospholipid. It kind of makes sense, right? Because phospho means phosphorus. Lipid is talking about the glycerol and the fatty acid parts. The only thing that really isn't in that name is the amine part, or the amino alcohol group that's in there. So they really should call these maybe amino alcohol phospholipids. That would be totally a complete name. But instead we just call them phospholipids. Now I do want to point out that you will, depending upon the book you read, see differences here. So if I take a look at that, sometimes that's written as just a PO minus. And again, remember that sometimes that's written as an NH3 with a plus. Because quite often when we're kind of taking a look at these molecules, we find that they are charged in the body. And then the other thing that you'll see them drawn often is that they'll... Oh yeah, we should, just to be complete, I guess you're right. This should be plus 4H2O to the reaction. You'll also a lot of times see them drawn where they flip around one side. So for instance, on this side, we might draw, oops, I got it backwards, since I was thinking backwards. That goes to our O, to our P, to our O minus, to our O. That goes to our glycerol, and then they'll show the fatty acids sort of on the opposite side of the molecule, meaning there's no set way to draw these molecules. And so people draw them all sorts of different ways, depending upon what they want to emphasize. For instance, this tends to emphasize the fact that this end of the molecule is actually quite hydrophilic. I mean, there's an NH3 plus group there. There's an O minus group there. There's a double bond oxygen there. There's lots of things there that are hydrophilic, whereas this end of the molecule is hydrophobic. And in fact, sometimes they won't even bother drawing that much of the molecule. They'll dumb it down, or I shouldn't say dumb it down, they'll actually make it look like this, where they won't even show all the parts. They'll just show one part of the molecule, which is sometimes called the head group, which is supposed to represent our hydrophilic part. And then they'll have these tail groups, which of course represent our hydrophobic parts. So sometimes they don't even bother drawing very much of it if they really simply just want to illustrate the hydrophilic and the hydrophobic parts of that. And I, of course, always think that looks like a sperm with two tails. Because, of course, how could I draw a fatty acid? See, they'll often draw fatty acids as a sperm with one tail. Because there's the fatty acid end, the carboxylic acid group, and then there's the alkane part. And so they'll sometimes draw them that way just because I would say they're lazy. So phospholipids, biologically, have that property of basically one end is very hydrophilic and one end is very hydrophobic. And so what we find is that these are used a lot of times for membranes or for, let's see, about 10 to 20% of the cell surface, cell walls, are actually made up of phospholipids. It's used as a sheath in nerve tissue and in brain matter. And so what it really does is it forms a protective layer between what we're trying to protect and what we're trying to do. Or for in the case of cell membranes, it's keeping track of all the contents inside the cell versus all the stuff outside the cell. There's also two other sort of things that we can kind of think about, and these And I don't know, this is, I'm kind of going a little out of order here just because it kind of seems to fit in. And, your book kind of organizes the chapter kind of funny in that it does introduces a bunch of the molecule, talks a little bit about their biology, and then talks more about their biology at the end of the discussion. And so I'm just going to put that section right here. And that's the difference between what we call a micelle and a liposome. It's 2 L's. I always thought they were called micelles at first instead of micelles. And micelles are formed from fatty acids, whereas liposomes are formed from phospholipids. And so what this is a good example, phospholipids, of how function follows form. Or so, basically how the structure of a molecule impacts its biology, I guess, biological use. And so for a micelle, remember, that's using a fatty acid. And so instead of drawing a lot of fatty acids, we're just going to draw it like this. Remember, that's our carboxylic acid. This is our alkane. And of course, for the liposome, we've got this. These are, again, just basically large alkane parts. And this represents our NH3 plus and our O minus parts. And so this is very hydrophilic. This is very phobic. And so what happens is they form different structures. Micelles tend to form circles. Well, I guess they both form circles, so that's a little silly to state. But they form a single layer with all the head groups, or all the tail groups, pointing in. And so they form a single layer that is hydrophilic on the outside and hydrophobic on the inside. And what these can be used for is to transport fatty acids or fats or oils all over the body. So normally these fats and oils, they don't dissolve very well in just liquid. So if you're trying to transport them around the body, and remember, this is our energy supply, this is where the body gets its energy from, then we have to actually pack them up inside these liposomes, or I'm sorry, inside of these micelles, so that we can transport them through the blood and then into the cells. Whereas if we take a look at liposomes, what we get is we get a double layer. So we've got an inner layer like this, and these are all pointing out. And then we've got an outer layer where all the tail groups are pointing in. And I'm not going to draw the whole thing, but what we get is a hydrophilic outside again. We get a hydrophobic middle layer. And then we get a little hydrophilic inner layer, or inner part. And so notice that they both have hydrophilic outer parts, right? But on one, the inside is hydrophobic, and on the other side, the insides are hydrophilic and actually contain usually liquid water, and they can be used to transport anything that's hydrophilic around the body. And so micelles and liposomes are used to transport things around your body. So here we have a double layer. And again, this is used to transport hydrophilic things. Why do we care about this? Why do we care about that? I don't care about any of that. Make sure we're not skipping anything. Hydrophilic, hydrophobic. Oh yeah, one of the cool things I think that's kind of neat as far as research that's being done for things like this is they're starting to use micelles and liposomes as drug delivery mechanisms. And so by tailoring, or by, tailoring, I saw Owen laugh, so we can sort of tailor make the outer coating of these, and so we can actually kind of target different parts of your body with these drugs. So instead of just giving you a drug and letting it go everywhere in your body, if we kind of put it in a micelle or a liposome and then we kind of tag it to go to a specific part of the body, you can use a lot less drug and have it be a lot more effective. And so this as a drug delivery mechanism is sort of a hot field of research. And it's not just using these basic micelles and liposomes. I mean, this gives you the general idea. They're modifying the head groups, they're modifying other parts of it so that it can be kind of taken to or attack only specific parts of the body. So I think that's kind of a neat little use for them. It's like you're packaging the pills inside a pill, almost. Okay, so that's phospholipid. The next two ones that we're going to draw are identical to phospholipids. The only thing that changes is the components in them. And so I consider these kind of the same exact topic with just minor changes. So let's talk about sphingolipids. So the only difference between a sphingolipid really and a phospholipid is that we use a molecule called sphingosine. And again, you don't have to memorize the structure of sphingosine. In fact, I don't have it memorized. I have to look up the structure of sphingosine in my book. And so sphingosine looks like this. It's kind of like a glycerol, but it's different in that it has a built-in chain at the top, and then in the middle carbon, it actually has an amine group, and then on the bottom carbon, it just looks like glycerol. So that's what sphingosine looks like. So instead of using glycerol as our backbone, we're going to use sphingosine as our backbone. And then, of course, we can have one fatty acid attached. And so, for instance, here's where we would put our fatty acid. And so notice, because sphingosine has that built-in part, has that top alkane part as part of the molecule itself, we only have one fatty acid in a sphingolipid instead of two. And then, of course, we have our phosphoric acid, or our phosphate group. And so we would have a plus HO-P double bond O-OH-OH. And then our last component of it is, again, just a nitrogen base. Or sometimes we call that an amino alcohol. And so, again, I'm lazy. I always pick the easiest one to draw because, well, like I said, I'm lazy. So I always pick, oops, that's not a very good drawing of it. We'll draw it with, make it sure it looks like it's two carbons, like that. And then can you guess how we put it all together? Minus H2O, right? And so in this case, when we're taking our waters out of it, you know, we actually have to take a hydrogen from our amine group, and we take an OH there, and we take an OH there just like we did. So we're really removing 3 waters from this molecule. And then when we draw our molecule, it's annoying because it's tedious to have to draw the sphingosine part. And then we have a C bonded to an N, C double bond O. Whoops. Wait. Yeah, that's right. N, C double bond O, fatty acid part. And then a C H2-O-P double bond O-O minus dash O dash NH3 plus is normally how you've seen it drawn. Plus, because Brittany's going to remind me if I don't put it there, 3 H2Os. Now, the bad thing is Jay noticed that his pen stopped working, which might mean the computer's going to crash. And since the PowerPoint's crashing right here, you'll have to imagine that I finish writing plus 3H2O, and you will have to write this down, and I'll reboot it here in a second. And then, of course, just like with a phospholipid, what part of that is hydrophobic and what part is hydrophilic? Yeah, and then that PO4, the NH3 plus kind of part is the hydrophilic part. And then the last thing I would have pointed out before I redrew it, because guess what, I'm not redrawing this when I reboot because that's like way too much work, is we also end up having what functional group here instead of our carbox or our esters. We now have a, what's it called? Amide. Okay, so let's just nuke that. Has everyone got it down, or should I wait? So the hydrophilic. Oh, come on, just disappear. Really? Oh, my whole computer is going to piss me off. Anyways, this part down here. That's the phosphate and the amine group. Ooh. And I get an electric shock. It's a good day. Kind of looking forward into a new building with hopefully a new computer that doesn't crash. That'd be like a bonus for Jay. Okay, we only have one small part to finish up, so we'll just draw a glycolipid next. In fact, I could probably just tell you how to draw a glycolipid because glycolipids are the exact same thing we've been drawing. Can you guess what's in a glycolipid instead of the regular stuff that we've been drawing? Okay, so the last part that we want to draw, or the last thing we want to draw, is called a glycolipid. Did you guys have a question? Okay, just curious. And glycolipids are basically the same as the sphingolipid and the phospholipids. In this case, we have sphingosine again. We, of course, have one fatty acid. We have a phosphate or phosphoric acid. And instead of the amino alcohol, we have a carbohydrate. And so that's where the glyco comes from, because remember, glycosidic means the bond between carbohydrates, and so a glycolipid has a carbohydrate in it. And so what we get for a general structure for those, I'm not going to draw the reaction. I think you guys have that point down now. We've got our sphingosine. Yes, this is just the end result. I think you guys have the process down, right? After you've seen it twice, I hope, plus practicing it a million times. And of course, I should point out that you can do, of course, the reverse, meaning I might give you the parts and tell you to build the molecule. I might give you the molecule and tell you to blow it up or take it apart. So then we've got our C, NH, C double bond O. Then we've got our C to an O, to a P, to a double bond O, to an O, and then to an O, and then where it's attached to the carbohydrate sort of differs. And of course, we should be careful because we know that things can be alpha or beta for various things, and that can be up and down. And so, you know, we've just got our normal carbohydrate there. I don't know which one I'm drawing here. It should probably be glucose or galactose, since those are the only ones your body really uses. But I have no idea if I drew glucose, galactose, or anything else. I guess maybe if I look in my notes, I should have one of these drawn. Nope, I'm so lazy in my notes that I didn't even bother drawing it. So I guess I'm just a slacker in that case. Sphingosine? It's just supposed to be one word. And so remember, sphingosine is kind of that part of the molecule. It's the glycerol backbone, but it's not glycerol, it's now sphingosine. And again, on your cheat sheet, all you have to do is figure out how to put these parts together and to be able to do minus H2O type reactions. You guys should all be masters of that. When I ask that question on the test, Jess, it should be like 3 points. Let's see. I think that's a good place to break. We have a tiny little bit of the chapter to finish up on steroids, and then what we'll do is we'll probably finish that up on Monday on steroids, and then the next chapter is amino acids, polypeptides, and proteins. So good luck to everyone on your tests in microbiology. For those of you that don't have a test in microbiology, have a good weekend.